All right, hey, so in class today, 215, we were looking at a homework question, and I started to solve it, and then I took a step back and made a comment that this might be something that we're actually going to get to later. It looks like it's a little bit out of place in chapter 1. We normally talk about this when we get to the unit on counting, because this uses something called the principle of inclusion-exclusion. But it's a question about sets. So this is question 1.2, question 8. And we're given some information about the makeup of the student population at a university. So we're told the following facts. The total university population is 16,000. So I'll use U to represent the set of all people at the university, and that's 16,000. We're told the number of daytime students, I'll call that set D. The number of daytime students is 9,000. We're told the number of students who are math majors, I'll call that set M, is 300. And that the set of graduate students, which I'll call G, is 1,000. Okay. We're also told that the number of day students who are math majors is 250. So what does it mean to be a day student who's a math major? It means you're in the set D and you're also in the set M. So we're told that this intersection, D intersect M, has a total of 250 students in it. We're also told that 50 of those people are graduate students. So if we look at the daytime math people who are also grad students, there's a total of 50. So the first part of this question is translating the information that's being given to us into a language of sets and set operations. Okay, we're also told there's 95 graduate mathematics majors. So if you're a graduate student and a math major, you fall in this set. You're in both G and M. We're told there's 95 of those. So we know the cardinality of that set. And the total number of daytime graduate students is 700. So if you're a daytime student and you're a graduate student, there's 700 of those. All right, and then we're asked to find some information, starting with the number of evening students. Okay, so let's think about Venn diagrams, right? Here's our universe of students. So this is the universal set. And here's our set of daytime students. If you're a daytime student, you're in this set. If you're not a daytime student, you're in this set out here, which is the complement of D. So to say how many evening students are there is asking us to find the cardinality of D bar. Well, the way that sets work, however many things we have in this set, and however many things we have outside this set, if we add those together, we should get the entire universe. So we have a pretty simple rule. The cardinality of D plus the cardinality of D bar should be the cardinality of the universe. And this is true for any set in here, so the cardinality of the graduate set plus the cardinality of the complement of the graduate set will be the cardinality of the universe. So our first few questions, we can use that basic idea. If we want to find the number of non-math majors, a non-math major means that you're not in the set of math majors, so we just want the cardinality of M bar, and that's going to be 16,000 minus 300. So that's 15,700. So these first few questions aren't terribly confusing. They kind of make sense intuitively if you think about it. The number of undergraduates, that's the cardinality of the complement of the set of graduate students. So the cardinality of G bar, and that's 16,000 minus the size of the set of graduate students, and that's 15,000. And so these were the calculations we were doing in class. And then around here, I started to realize this needed things we hadn't gone over yet. So part D asks for daytime graduate non-math major. So daytime graduate non-math. So we're looking for the count of students who are a daytime student, a graduate student, and not a math major. In other words, we want to know about students who belong to the set D, and also belong to the set G, and also belong to the set M bar. And we're trying to find the number of things in that set. All right, so intersections get tricky when we start trying to do cardinality calculations like this. So let's go back to a Venn diagram, but let's look at our three sets, daytime, graduate, and math majors. So here's our universe. Let's say this is the daytime students. These are the graduate students. And these are the math majors. All right, we're looking for daytime graduates who are not math majors. So we want someone who's in the set D and in the set G and not in the set M. And that's going to be just this little piece right here. Right? This whole little ellipsoid-like piece is D intersect G. But we want people who are in D and G but also outside M. That's going to be this piece here. But we can see that that's actually the same thing as looking at this piece and throwing away this part. Okay, so this big piece here, that's what? That's D intersect G. That's the set of everyone who's in D and G, regardless of whether or not they're in M. And this little piece right here, what's that? That's the intersection of D, G, and M. That's D intersect G intersect M. And so this whole ellipse piece here, D intersect G, is composed of two pieces. This lower piece, which is D intersect G intersect M, and this upper piece, which is what we're really interested in. So we can plug in numbers. D intersect G intersect M, we're told that's 50 students. And the whole intersection of D with G, D intersect G, we're told that's 700. So we have 700 students in here. We have 50 in this lower piece. That means this upper piece has 700 minus 50. That's 650 students. So D intersect G intersect the complement of M. This is 650. All right, so that gets a little bit hairier. Let's take a look at part E. So part E, we're asking for evening graduate students. So we're looking for students who are graduates and not daytime students. So G intersect D bar. All right, let's make another diagram. So here's our universe. Here's the set of graduate students. Here's the set of daytime students. And we're asked to find the number of evening graduate students. So we want students who are in G and not in D. So we're looking for the number of students in this funny shaped piece right here. And we can see that's equal to the number of things in all of G minus the number of things in this funny ellipse piece. Well, this funny ellipse piece right here is what? This is the intersection of G with D. So the number of things in this piece would be the total number of things in G minus the number of things that we're taking out of here. So it's the size of G minus the size of G intersect D. Well, the size of G we're told is 1,000, and G intersect D is 700, so this is equal to 300. So that's your answer for part E, 300 students. And then for part F, we're asked for evening graduate math majors. So evening means we're not a day student, we are a graduate student, and we are a math major. So now we're looking for the number of elements in D bar intersect G intersect M. Alright, well this is similar to something we just did. So here's our universe. Let's do D for daytime students, G for graduate students, M for math students. And we're looking for people who are in G and M but not in D. Okay, G intersect M is this whole wedge here, and we want people who are not in D, so we're looking for this piece right here. And the cardinality of that, the number of things in that, will be the number of things in this bigger wedge, which is just G intersect M, minus the number of things that are in this piece right here, the number of things we want to throw away. Well, what is this funny three-sided shape right here? This is the intersection of D and G and M. The stuff in here is exactly the stuff that's in all three of those sets. And how many things are in there? It's just the number of things in D and G and M. Alright, and we have that data. The number of things in both G and M is 95. The number of things in D, G, and M is 50. And so this leaves 45 things in this piece over here. So the number of evening graduate math majors is 45. Alright, and then the last question, which was the part that the person who asked was most interested in, question G, we're looking for evening undergrad non-math majors. Alright, so this is the really sneaky one. So we want evening undergrad non-math. Okay, well we know the number of evening students is 7,000, the number of undergrad is 15,000, and the number of non-math is 15,700. Okay, at first thought we might be tempted to add those together. But if we do that, we're going to get something bigger than 30,000, and we only have 16,000 people in the university. So just adding these is not exactly what we want. But this is where we're going to come to the principle of inclusion-exclusion. So let me talk about this in general first, and then we'll apply it to the problem. So suppose we have a set A and a set B. And suppose A has 100 things in it, and B also has 100 things in it. And we can ask, what do we get if we take the union of A and B? How many things do we end up with? Well, we might think the answer is 100 plus 100. But remember, if we were to write out the elements of this, and then take the union, we don't necessarily list all the elements in A followed by all the elements in B for 200 elements, because we don't have duplicates in sets. Right? We wouldn't write an element twice if it occurred in both A and B. So when we're taking the union of things and we want to count how big that union is, we need to take into account how big the intersection is. And here's what it turns out happens. If we take A and B and put them together, well, we're going to take everything from A and put that in our union. We're going to take everything from B and put that in our union. If we just count up the number of elements in A and the number of elements B and add those together, anything that's in the overlap is getting counted twice. Anything that's in both A and B is going to be counted twice if we just add up the size of A and the size of B. So to get the size of the union, we actually need to add the sizes of A and B, but then subtract the size of the intersection. So that's the principle of inclusion-exclusion. And I'll give you an example. Suppose A is the set 1, 2, 3, 4, and B is the set 2, 3, 4, 5, 6, 7, 8. Okay, number of things in A is 4, the number of things in B is 1, 2, 3, 4, 5, 6, 7. The union is 1, 2, 3, 4. Well, let me write an illegal representation of this. 1, 2, 3, 4, 2, 3, 4, 5, 6, 7, 8. How many things have I written down? 1, 2, 3, 4, 1, 2, 3, 4, 5, 6, 7. I've written down 11 things total. And if I didn't think about it deeply, I would say, okay, the number of elements in A union B is 11. But we know that's incorrect because we're not supposed to write elements more than once. So I have to throw away some of these elements. Which ones got written twice? The elements that are in both A and B. So if I look at the intersection of A with B, this contains 2, 3, 4. There's 3 elements in there. Well, sure enough, one of these 2's, one of these 3's, and one of these 4's have to get thrown away. Now I have a proper set. How many things do I have in it? 1, 2, 3, 4, 5, 6, 7, 8. I started with 11 elements. I threw away how many things? 3. Why 3? Because there were 3 things in the overlap. So take the size of A, the size of B, add those together, but then throw away the size of the overlap. That gives you the size of the union. All right, so that's a general rule we can use when we want to find the size of the union of 2 sets, add up the sizes of each set, throw away the size of the intersection. So that's almost enough to do this last question. Because we know the size of these 3 sets, right? The evening students, the undergrads, the non-math majors are 7,000, 15,000, and 15,700. And we know the intersections of these also. But we have 3 sets we have to take the union of, and the union of 3 sets is a little more complicated. So I'll get a little hand wavy with this. So here's a set A, here's a set B, here's a set C. The size of the union is equal to the sum of the sizes of A, B, and C. Okay, but anything that was in both A and B just got counted twice. So we have to take that off. And anything that was in A and C got counted twice. And anything that was in B and C got counted twice. And we're almost done, but we're not quite there. All right, so let's check our work so far. If there's something that's just in A, it'll get counted right here. It won't appear in any of these other sets. If there's something that's in, say, A and B, but not also in C, it'll get counted in A, it'll get counted in B, and it will get subtracted off once here, so it'll be counted a total of once. That's correct. But if there is an element that's in all 3 sets, A, B, and C, how many times have we counted that? We counted it for A, we counted it for B, we counted it for C. And then we corrected our count by subtracting it once because it's in A intersect B. We subtracted it again because it's in A intersect C. We subtracted it a 3rd time because it's in A intersect B. Sorry, this should be B intersect C. We subtracted it a 3rd time because it's in B intersect C. As it stands right now, anything that's in the intersection of all 3 sets has not been counted in our final count yet. So we have to add the size of the intersection of all three sets. And that's the principle of inclusion-exclusion for three sets. It's hairy, but it works. All right? And if we accept that, and we'll see this again in a later unit, right? If we accept this fact, then we can solve our last part of our problem pretty easily. All right, so I'm going to rephrase this problem. We're looking for evening undergraduate non-math majors. So we're looking for the number of students that are in the complement of the daytime group and the complement of the graduate group. I don't know why I'm using C's here. Complement of the daytime group and the complement of the graduate group and the complement of the math group. And we want to find how many people are in this set. All right. Well, this whole rule of inclusion-exclusion is talking about the union of sets. And here we're talking about the intersection of sets. And we're talking about the intersection of the complements of sets. So we're going to punt to our friend De Morgan. And we're going to use De Morgan's rule on three entities. And we're going to say that this set is the same as the following: D union G union M complement. So the intersection of the complements is the same as the complement of the unions. And so to answer this last part of the question, we're going to find the complement of the students who are both daytime, graduate, and math-seeking students, all three. All right, so this is another wrinkle. We're trying to find the number of people who are not in D and not in G and not in M. Instead, we're going to find the number of people who are in D or G or M and take the complement of that. All right, so let's solve this subproblem. Let's find the number of people who are daytime or graduate or math majors. All right, so here's our set. Here's the daytime students, here's the graduate students, here's the math students. We're looking for how many people are in any or some or all of these sets. And then the answer to our question will be the size of what's outside here. So it'll be 16,000 minus this answer. Well, we can directly use the principle of inclusion-exclusion. So let me write this out on a clean sheet of paper. So the number of people who are in D or in G or in M will be the following: the number in D plus the number in G plus the number in M minus the number in the three intersections plus adding back the number who are in all three. And that'll be the number of people who are either day students, graduate students, and or math majors. All right, well, I think we have most of this information available. So the number of daytime students is 9,000. The number of graduate students is 1,000. The number of math majors is 300. All right, minus the number of daytime graduate students, which was 700, minus the number of daytime math majors, which was 250, minus the number of graduate math majors, which was 95, plus the number of daytime graduate math majors, graduate math majors was 50. Okay, so that's 10,300 minus 950 minus 95 plus 50. So I might get the answer wrong, but I'm going to do this by hand anyway. So 10,300 plus 50, 10,350 minus 950 is going to be 0, 0, 4, 9400 minus 95 will be 9305. That's the number of students who are daytime or graduate or math. So the number who are none of those, which means they are an evening undergraduate non-math, will be 16,000 minus 9,305. And that's going to give us 6,695 modulo arithmetic errors. So that would be your answer for F. So as they say in math classes, see, it's trivial. It's really not. But that's how we go about doing this. So the first few you can kind of intuit your way through. The remaining questions up through the last one you can think about if you just sort of think about intersections of two sets and how we can find the size of something outside that intersection. But then the last one is really tricky. Okay. So the book text talks about that. If you Google inclusion, exclusion, you can find that. And we'll come back to it and visit this later. But anyway, that's the solution to that question. All right, thanks.